Bueno, segunda.
This is the second session of the conferences in the TecnoRevolution cycle from Fundación Telefónica in collaboration with Obra Social La Caixa. Thank you so very much for being here. I think we have a full house. The occasion well deserves it. We're going to hear very interesting things tonight. Perhaps you attended the exhibit already that we have for TecnoRevolution on the 3rd floor. If you haven't been there, you should. And over there, you will learn about the amazing technological development of this science that has really done a lot of things for sciences. It's given it a different twist, and it's made many of the sciences take off in many aspects. And up there, you will be able to move objects with your mind, and likewise, we will be able to measure your brain waves. And thus you will get to learn the brain power and the power of the nervous system, which is one of the topics that our speaker is most interested in. He is Kevin Warwick. He is an expert in cybernetics in the Reading University in the UK, and he's known as Captain Cyborg by the media. He is an expert in the interaction man-machine, and he says that our body is a hurdle for our brain. As I said, he's going to tell us things that are going to leave us astounded. So without further ado, welcome Kevin. Go ahead with your talk, and please surprise us all. Surprise us all.
And thank you for the invitation across here to Telefónica. And really this is about experimentation. I've called it the Cyborg experiments because it's very much looking at practical experimentation that either has happened or is happening. So this is, yes, it may sound a little science fiction to some of you, but it's very much science. This is what has been achieved, this is what is being achieved, and hopefully you'll be able to get inspiration from that and get an understanding of what could be possible in the future. So it's different experiments, and from those we can look at how people perhaps can be helped if they have a medical problem, but also how all of us could be better, could upgrade, could be enhanced. And I think that's one of the principles here, that as humans we're all pretty limited in what we do, particularly mentally, but that's just at the moment. With the help of technology we can be much better. So, straight into the first experiment, which now, it has the term biohacking. This is something that various people are having a go at. But when this is me, or a younger version of me, and this is my doctor, and this was in answer to various science predictors, science gurus, who were saying that in the future we won't need keys for our cars, we won't need passports. What we will have is a little implant that identifies us to the system around us. But nobody had actually tried it until I did. And this is what was implanted, not the thing on the left-hand side, that's not what was implanted, but on the right-hand side is a radio frequency identification device that simply identified me to the computer in my building. So the computer knew where I was at particular points. So what we got it to do, as I walked around my building, down the corridor, the lights came on. Towards my laboratory, the door opened for me automatically. It was great fun. Coming through the front door, the computer said, "Hello, Professor Warwick." It was nice to get a welcome in the morning. Various people criticized me at the time and said, no, we're never going to want to have anything like that. Whereas now in America, for example, this is one example, a lot of people who have diabetes or epilepsy have an implant of this type, so that when they go into hospital, the authorities know by looking at the information on the implant what medication the person needs. You know, it could even be life-saving in certain circumstances. I think one of the biggest examples of where the technology is used, though, is in cats and dogs. I don't know, does anybody have a cat or a dog that has a chip implanted? I see you nodding your head. Those various people. Yeah, there we go. Everybody. Does anybody not have a cat or a dog with a chip in? There's one or two in the minority. Well, I think for those that do have, you can feel happy that the technology was fully tested on humans before your animal received the lots of examples of where the technology is used now, and we're probably going to see many more. But there are lots of people trying it for artistic purposes as well as scientific purposes. And that brings me on to the next experiment, which I'm calling sensory substitution. We'll see why in a moment. Partly this is on the basis that humans have 5 senses. We have a limited sensory input. There's a lot of signals out there. In here, there's lots of signals, such as infrared signals, ultraviolet signals, X-rays, which as humans we don't perceive. We don't sense those signals. We just miss out on a lot of what's going on around us. So can we improve? Can we upgrade? So I should perhaps say, don't try this at home, but maybe you do want to try it at home. I don't know. I now have 3 students that have magnets implanted in their fingers. If you don't like the blood, there's going to be more later on, so be prepared. This is a picture of one of my students getting the magnets implanted. Now, we have a slight problem here because we have to get ethical approval from the university to do this research, these trials. And you may notice the guy that's carrying out the procedure has tattoos on his arm. You may see the tattoos. And that's because he is in fact a tattoo artist. That's his job. And he goes by the name, this is on his website, he calls himself Dr. Evil. Now this presents us with a problem, because in the University of Reading we have to get ethical approval, and there is a line on the forms which says who is carrying out the medical procedure. And we have to write there Dr. Evil, which makes things very difficult for us, I have to say. But he's very good at what he does, and as I said, I now have 3 students that have these implants. Here's an X-ray of the magnet, so 2 magnets. It's in the left hand because the students tend to be right-handed, and if anything goes wrong, so far it hasn't, but if anything goes wrong, it's to the left hand, not the right hand. But the magnets are there. And then we see what we're doing with the magnets. Now, this is Jawesh, who was the first student to have them. And we see on the baseball cap ultrasonic sensors. You see on the peak of the cap are ultrasonic sensors, which it's a bit like a bat sensing the world. They give an accurate indication of distance to objects, how far objects are away. So as an object comes closer, or as the person moves closer to an object, so the signals from the ultrasonic sensors change, and those signals are sent down. Perhaps you can see on his finger is a little coil of wire around the finger. So as an object comes closer, the current in the coil changes, and that causes the magnet to vibrate more the closer an object is, or to vibrate less as an object moves further away. So essentially the distance to an object is being changed into a vibration in the finger. And hopefully you can see, for somebody who is blind, they could have one of these magnets in their fingers and they would get a good indication of distance to objects, dependent on where the sensors are positioned. But for our experimentation, it's like extending the sensory range. It doesn't have to be an ultrasonic sensor. Ian Harrison, another of my students, he's doing a PhD with me, and he has been experimenting with infrared sensors. Now, infrared is like a heat signal. So what he can do is to detect how hot a body is, how hot an object is from a distance. So he can, sorry, just to use you as examples, he can test and say, you are hotter than you are, in a temperature sense. Get me into trouble. But he can detect how hot objects are from a distance because of the vibrations in his fingers, which is not a sense humans have ordinarily, but it's a sense, if anybody wants to detect how hot an object is from a distance, we have the technology to do that. Now it's something you can do. All you have to have is a little magnet implanted in the finger, and there's nothing more to it. Here's something a little bit different. This maybe Telefónica would be interested in this. It's a different form of communication. This is Ashley, another one of my students, and on the little pad there are a number of electrodes which you put on your tongue. And what this does is to send small currents, electric currents, into the tongue, and in that way you can communicate with the human brain very rapidly. This is a very rapid way of communicating with the human brain. It can be much faster than visual input. So you can send letters and shapes, also directions, or you can send yes, no, or right, left, all sorts of information in to the person's brain via the tongue. And it's interesting, if any of you have had children or seen children, when a child is very young, they put everything into their mouth to learn about it. They're learning about textures and all sorts of things. I mean, we don't know half of what they're learning. And for some reason, as the child gets older, they stop doing that. But clearly, we have sensors on the tongue that can be used to send signals into the brain. And one of the companies that is sponsoring this particular research is Nissan Motor Corporation. And partly this is to try and send signals into the driver's brain as quickly as possible for safety purposes. It doesn't have to be anything that big, but potentially some little thing that you can put on your tongue that could save your life, because it could send signals to say there is a car overtaking you, or somebody has just walked out into the road, or whatever it happens to be. It could send signals not visually, but straight to your brain, much faster to your brain via the tongue. So it's looking at different potential to communicate with the brain in a more accurate, more rapid way. Part of it, I guess, is also asking questions about what it means to be human and what we could potentially do. Now, the next section is a little bit different. Culturing neurons. Neurons are brain cells, and culturing means growing. And that's what we're doing here, growing brain cells. Till now we've been looking at taking a brain and changing it. Now we're looking at growing brains. Now, just to get us into this, we're dealing with growing brains for robots, giving robots brains, essentially, of the type of brain that we are used to. But I want to introduce you, first of all, to some of our robots. And what you're going to see is, this is a clip from a BBC program called Inventions That Change the World. There's a prize if you recognize the presenter of the program. But what you'll be looking at, first of all, is a robot head called Morgui, and we're researching there to integrate the senses on Morgui in artificial intelligence. More importantly for this presentation are the small mobile robots that you'll see later on. So there is sound. Hopefully the translators will be able to give you an idea what's going on here.
One of the AI community's leading lights is Professor Kevin Warwick.
Well, this is a robot head.
Dissatisfied with vacuum cleaners and robot dogs, Kevin's gone one stage further. His cyborg comes complete with
radar in its nose and an infrared top lip.
Is it intelligent?
Well, in a very limited way, I guess it is. It's sort of a basic instinct. What do I do with this information that I'm getting? How do I move? How do I operate if this signal is different?
So what's it doing now?
Well, if you clap your hands...
Oi, over here. Oh, it did it.
It's making basic decisions. All we've got it doing here is programmed to make basic decisions based on that sensory information that's coming in.
Getting the information in is nothing. That's like picking up a book. That's not an intelligent thing to do. Reading the book and knowing what the words mean, that's surely the intelligence.
Many machines can read books nowadays, but it means something different electronically to the machine as it would mean to a human.
Though the cyborg head does a reasonable job of sensing, it can't really interact with or explore its surroundings. It's fastened to its robot arm. And according to Kevin, it's only as intelligent as a dishwasher. If that's a dishwasher...
Yes.
Where are these in terms of... Are they dolphins, chimps?
I think you'd have to say it's about the 50 to 100 brain cell area. So realistically, you're talking slugs and snails.
But a slug and a snail, they know to eat. They know. These things don't...
They have some innate abilities.
There's no self-preservation with that.
Well, we do have. The power supply, they don't have their own batteries. They each have power they're picking up from the floor here. That's where they're getting their energy. That's where they're getting their food
But
from.
if you turned off this section of the floor,
if we turn off this section,
was here,
they have a basic instinct to go and look for some power somewhere else.
They
will
that.
keep going to do that until they find some.
So if I put him down,
it should go off.
So he'll have to go and look for power. And you've got to tell him to do that.
No, it's an innate response for that robot. It's a basic thing of its life. Yeah, yeah.
No, his lights have come back on.
Lights are coming on.
So he's found power.
It's happy now that it's getting power. Away to go.
But these then are as intelligent as slugs.
It's different. But in terms of numbers of brain cells and that sort of thing, yeah, we have slugs. Probably you could say we're up to bees and wasps, the sort of tens of thousands of brain cells, is about as good as you can get. Yeah.
Bees and wasps.
Yeah.
Right.
So those robots we were looking at there have computers, microprocessors for the brain. And with that we can look at how they learn, and how they communicate, how they interact, so all sorts of interesting scientific things. But what we've done more recently is to replace the computers in their brains with biological brains. So on the picture you can see, the box on the right-hand side, I can move like this, can't I? Here we go. The box on the right-hand side is the technological robot. That's the robot body. So what we were looking at, it has wheels and it has ultrasonic sensors, the same sort of ultrasonic sensors that we were looking at before. So that's the technological body of the robot. But the brain, we've now removed the computer and you can see a biological neural network. Neurons are the brain cells. And it says here MEA, this is a multi-electrode array. It's actually a little dish with electrodes, pieces of metal on the bottom of it, which we can send signals into and pick up signals from. And what we put in the dish are brain cells. Either we take them from rat embryos, or we can actually buy in human brain cells. Either are possible. And what we can do, this is the MEA, the multi-electrode array, and these terminals here where we can connect onto and send signals into the culture, into the brain that is growing. The black rings are there to stop the brain dehydrating. It has to be kept moist. It's kept in an incubator because it's living tissue at 37 degrees centigrade. We have to keep the temperature constant. We have to feed it with minerals and nutrients, a little pink liquid on a regular basis. Every couple of days it needs to be fed because these need to digest food, they need to live, as it were. And after about 10 days we can then look at using it. Now it's interesting with brain cells, with neurons, when we put them into the dish, first of all they're not connected at all, but within a few minutes they start to put out what look like tentacles. We can see this happening under the microscope. And within 20 minutes they start to connect up with each other and become what are called dendrites and axons, inputs and outputs to the neurons. So this is a basic property of neurons, of brain cells, is to link up with each other. This is what they do automatically, genetically if you like. They link up with each other and start to communicate. That's what brain cells do. So it amazes me when some people grumble about children using Facebook and things like saying, why do children want to use Facebook and communicate that way? Well, they can't do it. It's communication. That's what their brain cells do. This is what's happening. They're just a bunch of brain cells, so they're doing what their brain cells do. And this is what the neurons do, which is fortunate for us because after about 10 days, the neurons have connected up, and in this array there are about 150,000 brain cells, so it's reasonably complex, and they will connect up. We have a complex network after 10 days, and we give it a body at that time. So what we want the robot to do is to move towards the wall, to detect the wall ultrasonically. The signal of that detection passes through the brain, ting, like that you saw, and the robot turns right. The decision to turn right, there was no computer involved with that, and it got it wrong. But this is a baby brain. This brain is only 10 days old, so some of the time it gets it right. That was perhaps early. Then it changes its mind and turns around. It wasn't supposed to do that. And now it detects the wall and turns right. That's great. And then it detects the wall but didn't turn. But it's just a baby brain. Now the beautiful thing about this is that it doesn't really matter when it gets it wrong. Every time it gets it right, that particular pathway that made the decision, the pathway in the brain, strengthens. Physically it strengthens. And if you can imagine here, it gets it right maybe 15, 16 times while we're watching it. Every time it does that, the pathway through the brain strengthens. So this is the process of habitual learning, doing something by habit. The pure thing that when you do something, and when you do something, and when you do something, the pathway through the brain becomes so strong that you almost can't do anything else. Maybe for those of you that drive, you drive a particular route day after day after day, and you get, oh, I wasn't even thinking, I've just driven and I didn't think about it. Well, the pathway through your brain was so programmed in this way through habit that you probably didn't need to think deeply about it. And this is the exact thing we're looking at here. and we can see under the microscope the changes occurring in the brain as they occur. So that was 10 days. We're now going to skip ahead in time. This is the same robot, the same brain, after 2 months. And all it has been doing is 1 hour every day. It's been doing that particular process. And we've been able to look at how that particular type of learning has occurred. So it detects the wall and turns right. Pretty boring, but that's all we want it to do. And we'll see here, this one, I've taken a good example, I have to say. They don't all work out that well. But as you can see, it detects the wall and turns right. So now it is very different from its performance earlier on. It's learned. This robot has had a university education. And fine, and we can watch, and it is a little bit boring because it doesn't make any mistakes, this particular one. We have examples where the same brain tissue, but they've learned a little bit differently. Sometimes they can be a bit aggressive, sometimes they can be hesitant, sometimes no matter how much you tell them, it still doesn't seem to listen. It's obviously based on my wife's philosophy, but so you can see here, and we can look at how robot brains learn, and some of the things we're trying to do here is to try and work out how memories actually form in the brain, to put the robot in particular positions and try and see how the memory of that position and what to do about it, what it looks like in the brain and how does it recall the memory. Because if we can figure that out, then potentially we can add brain cells or add stem cells to try and help it retain the memory and therefore start to tackle things like dementia, which we really don't understand what's going on, what the problem is. The latest with this, we're now growing the brains not just in 2 dimensions but in 3 dimensions, and that gives us approximately 30 million brain cells. So we are dealing here, to be clear, we have 30 million human brain cells in a robot body. That's what we have now. So if we start to make it bigger and give the robot more things to do, then hopefully you can see where the future is, a different type of cyborg. Now, the next one, next area, is something some of you might be familiar with. It's more for medical, for therapeutic purposes. And deep brain stimulation, as I'm going to describe, mainly it's used to help people with Parkinson's disease, to overcome the effects of Parkinson's disease. But it is also useful for people with epilepsy and even people with clinical depression. The same technique is being used with the implant in a different position. For Parkinson's disease, what the surgeon does is drill a hole down into the center of the brain and position the spindle, which has about 4 or 6 electrodes. You can see the red area is where the electrodes are. The modern versions have 6 electrodes, and the surgeon positions those in possibly the thalamus, with a tiny part in the center of the brain, or the subthalamic nucleus. It's an alternative place to position it. And it may depend on the patient, also depends on the surgeon. Now this would be if somebody just has Parkinson's disease on one side, but very often the person has it on both sides, and so they would need 2 implants, one in one side of the brain and one on the other. So what you're going to see is a genuine patient who has Parkinson's disease. The effects of chemical treatments, the dopamine, which is the typical chemical treatment, the effects of that have worn off. So really he's in a pretty awful condition. And he's received 2 of these electrodes positioned in his brain, and you'll see the assistants switch on the power packs. The power packs are actually positioned here, you know, for the humans, in fact, we don't really have much of our body in here. This is perfect places for putting pieces of technology, and the power packs are positioned here. Inductively, you'll see the assistant switch them on, and there are wires underneath the skin running into these electrodes. So you'll see how the person is with Parkinson's disease, and then how the person is, in this case, with purely electronic stimulation of the brain. In this particular clip, he doesn't have any chemical medication as well.
Of Mr. Plessman when he was referred to us by his neurologist in Belgium, and you see him before surgery without drug, unable to stand up by himself. He's helped by Patricia Limousin, who is a neurologist in our group, and he's not able to do anything of, as he will tell you, makes your life looking like normal. He's not able to walk. He has having dystonia, which are muscular contraction, deforming the different joints, and this is the best he could do without the drugs, with the help of people around him and maybe his wife and friends. He was referred because the drugs were not working anymore. He was not having any more improvement, and as he will tell you, he was just stuck to a wheelchair. This is after surgery. You see the tremor. We turn one of the two stimulators which were implanted with electrode into his subthalamic nucleus, which is a tiny part of the brain, and we see that in a few seconds the stimulation induces a stop of the tremor. This is still visible on the other side. We will turn on the stimulator on the right side, and you will see something even more spectacular than that. You will see that the patient feels again free, and he reset himself in his chair in the position where he feels the most comfortable. He will obey Dr. Pollack in doing some tests, even if he feels that those tests are a little bit useless as compared to the feeling he has. He can do that almost normally. On the right side, should I do it longer, does he say? And he will show it on the other side. And then he will walk. He stood up alone. He's without any drug. You see him walking, turning. It was a few days before the Vienna meeting on movement disorder.
That's really showing how well it can work. But one problem with the technology is that it's using a lot of electrical power, using a lot of electrical current. It's applying stimulation all the time. And after about 2 years, the power packs have run down and they need to be replaced. So we're working with the surgeons at the Radcliffe Hospital in Oxford to make the stimulators intelligent. So they only stimulate when they need to stimulate, not all the time. So what we're doing, the electrodes in the brain, we're taking information about the electrical activity in the brain and feeding it into a computer. And the computer, which has an artificial intelligence system as part of it, learns to recognize the electrical activity in the person's brain and to link it with the tremors and the muscle locking. Now, not only that, but because it's a computer system, it can predict when the tremors are going to start before they start. Accurate to about 20 seconds before they start. So essentially the patient could be okay, and the artificial intelligence system will say in 20 seconds time tremors are going to start, and then the stimulating pulse is applied only then, when the artificial intelligence system says so. And that's what we're working with the surgeons for, perfecting at the moment for people, to make the stimulator a little bit more intelligent. The one sort of side product, this wasn't what we were intending to do, is that the artificial intelligence system is really categorizing the electrical activity in the brain into different boxes. So what it appears is that there is not just one Parkinson disease, but there are different types of Parkinson disease that the computer system is able to pick up on. And now we're doing more research. In fact, I have a student at the, I'll get the pronunciation correct here, it'll be translated, so that's okay. At the University Juan Carlos III, just outside Madrid, and she is helping with that work. So a PhD student who is just nearby here that is working on this computer understanding of the activity in the brain. So the computer knows better than the human themselves what's actually happening in the brain for medical purposes. And now, maybe the bit you've been waiting for, rather than treatment for somebody who has a problem, we look at enhancement for all of us. Let's use this technology to give ourselves more extra abilities. And if you can't think, if you think you're perfect and you don't need anything extra, well, think again. Clearly memory, computer memory is absolutely phenomenal. Wouldn't you like to have a much better memory? Well, if you link your brain with a computer, potentially you could have. Sensing, the third one, we've already looked at to an extent. Sure, we can have more senses if we want. I think the biggest thing of all for me, though, is communication. Because when you look at how humans communicate, it's almost embarrassing that our communication is so poor compared to technology. I mean, never mind the translation that we're having to do here. What actually happens in a human brain? We have electrochemical signals. All our thoughts and our original ideas, feelings, emotions, all of that is electrochemical signals in the brain. And if we want to communicate, sorry if this is going to put Telefónica out of business, but if we want to communicate, we convert those signals from electrochemical to mechanical, pressure waves, or mechanical movements if we're typing in. And those signals travel slowly. The pressure wave is full of errors, doesn't travel very far, and somebody's ears will convert the signals back from mechanical signals to electrochemical signals. And of course, even if you've been married 30 or 40 years, you still, what is she trying to say to me? I don't understand at all. If we could just send signals directly from brain to brain, we would be able to communicate in a much more powerful way. Not just some sort of language, but in terms of feelings, emotions, thoughts, ideas, basic concepts, colors. We'll be able to communicate in a much richer way. When Telefónica does it, I want at least 10% of the proceeds. That's and if they don't do it, they'll go out of business because everybody will be doing it. So let's go with that enhancement. This is Campbell Aird, who lost his arm due to cancer, and he's been given this robot arm, but you'll see him flicking the switch with his human hand to control the robot arm and hand, which, there he goes, flicks the switch. Which is a bit silly, really. What we would prefer is for him to control the arm from his brain and to feel what the hand is feeling in his brain. And for that, we need an interface to link his brain, his nervous system, with the wires and back from the wires to his nervous system. And this is my main area of research. Let's assume we can do it. Let's assume we can take brain signals, put them onto wires, pick up signals from the wires, pass them to the brain. Sure, we can give somebody an artificial arm or an artificial leg, but we can do much more. Because if we put signals on wires, this is what Telefónica is all about. We can send the signals wherever we want. But now we're talking about brain signals. So we can send those brain signals across a network. As far as the person's concerned, it's their body. At the part of the network you could have not an arm or a leg attached to your body, but you can have an arm or a leg on another continent or on another planet. And that arm or leg can touch and feel, and those signals can be sent back across the network directly to your brain. So what we're talking about here is, with this technology, your brain and your body don't have to be in the same place anymore. That's just how we've evolved to have that limitation. But with technology, that doesn't have to be the case now. Your brain can be in Madrid, and your body can be in London, Geneva, Hong Kong, wherever you want it to be, and on planet Mars, wherever you want your body to be, that's where it can be. So what have I done? Here is me on the operating table at the Radcliffe Hospital in Oxford. This was a 2-hour operation. I didn't need it for medical purposes, but I did need it for scientific purposes. There were 4 neurosurgeons involved, and what I had implanted was this. This is, again, it's a type of array, and this was fired into my nervous system. It's got 100 electrodes on it, so I had 100 electrodes fired into my nervous system. I promised you a little bit more blood, and here we are. Sorry about that. This is my arm. This is the same arm, and what the surgeons did was to make 2 incisions, 2 cuts. They then put that tube that you can see up my arm. They then pushed that array, the 100 spikes, up the tube. They removed the tube, hammered the spikes into my nervous system, just by there, and then stitched everything up. For 3 months I had the electrodes in my nervous system, wires running up my arm, coming out onto this connector pad we can see on the right hand side. So those little gold terminals here, ding ding ding, were connected into my nervous system electrically, and therefore to my brain electrically, because the nervous system operates in that way. So we could then plug those terminals into the computer, or to send the signals by wireless from my nervous system to the computer, and back the other way, because this works bidirectionally. So we could send signals from the computer into my nervous system to communicate with my brain in a different way. So I've got a little clip now from Discovery TV. Hopefully the translators can have a go at picking out the main points here, but you'll see the visual images, and then I'll pick up to describe the experiments in a little bit more detail. The sound on it.
Part man, part machine. Kevin Warwick, Cybernetics Professor at Reading University, England, took a leap into the future as long ago as 2002. For 3 months, a silicon chip was implanted into the nerves in his arm.
At that time, no human had had an implant of this type before.
It was a procedure that until then had only been tested on chickens.
Would the body reject it? Would it affect the way I moved, or my sensory capabilities? I could have lost the use of my hand. Could it affect my brain? Ultimately, could have sent me crazy.
Kevin was plugged into a computer which monitored the nerve signals from his brain to his arm, receiving and transmitting them as radio waves. With the signals from his brain, Kevin could not only turn on lights, he could control a wheelchair. And from 5,000 kilometers away via the internet, he succeeded in getting a robot hand to mimic his own hand movements. His most impressive experiment involved his wife, Irena, also having a chip implanted in her arm.
The communication experiment between myself and Irena was vitally important to me. This was the highlight of the whole experiment.
Kevin wanted to discover if it was possible for his brain to receive and feel signals from Irena's brain.
When Irena first moved her hand, it actually felt like a charge running up my index finger. It was a phenomenal feeling. Literally, every time she moved, my brain received a signal. There we were communicating for the first time in the world, nervous system to nervous system.
It was the first time two people had electronically communicated by thought alone.
In the short term, we're going to see implants used to help people who are paralyzed switch on lights, operate the TV, just by thinking about it.
In 30 years, he believes we'll all have chips in our brains.
But ultimately, having extra memory, having downloads from the computer, uploading from the brain. Earth is going to be controlled by cyborgs. Humans are going to be something of a subspecies.
We'll be half man, half machine, with super memory, super senses and superpowers.
I think quite clearly that's where we're going. Superhuman. A little bit of Nietzschean philosophy to finish with. Just a few holiday snaps to describe particular parts of the experiment. This is to do with sensory input. Again, the baseball cap I'm wearing has ultrasonic sensors, and this time the output from the ultrasonic sensors was fed down into my nervous system. So essentially, as objects came closer, my brain was receiving pulses that increased in frequency. The closer the object, the more pulses. We can see with a blindfold on, I was able to detect objects and move around. And it's a big advantage. The human brain is very adaptive, very plastic, and so it can take on new sensory input. This is my wife, Irena, helped in a number of ways, and she's wearing some jewellery that a student at the Royal College of Art in London put together. And the jewellery changes colour from red to blue, and it was linked to my nervous system. So signals from my nervous system dictated what colour my wife's jewellery was. And now if you can imagine the scene, I am calm and relaxed, and my wife's jewellery is blue. I am excited, my wife's jewellery flashes red. She doesn't work in the university, she works in an office differently, and there she is in her office, the jewellery is blue, fine, he's not doing anything he shouldn't, and then the jewellery starts flashing red. What is he doing? And more importantly, who is he doing it with? Maybe not such a good idea, though. This was taken in Columbia University, New York City, and the computer science team there helped us put my nervous system on to the internet live. So it actually had an IP address, my nervous system, and we linked up with the robot hand in England. So there was me in the United States and the robot hand in England. And what happened, I opened and closed my hand, and my brain signals, as well as doing that, was sent across the internet to open and close the robot hand. So my brain signals were operating the robot hand as well. And when the robot hand gripped an object, signals were sent back from the fingertips in the robot hand across the internet to stimulate my nervous system in New York. So I was receiving pulses of current that increased the more the robot hand gripped an object. And what I was trying to do was to open and close my hand to effectively open and close the robot hand, so it just gripped an object, like holding on to an egg. So not too much pressure, not too little. And that was very successful. So it was extending my nervous system across a network. And then the final part of the experiment, my wife, again, I should suggest not to try this, but if you want to, she had 2 electrodes pushed into her nervous system by the doctor from the outside. If you do try this, you will find it is extremely painful. And she thought, and I thought she was going to have anesthetic for this, but the doctor said, no, 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 I need to make sure that I've made a good contact. So she screamed a little, but there we go. 2 electrodes, and we went back to the laboratory and linked our nervous systems together electrically. So every time she closed her hand, my brain received a pulse. So when she went duk, 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 3 pulses or whatever. So what we were doing, and back the other way, if I closed my hand, then her nervous system was stimulated. So what we did was to communicate directly from nervous system to nervous system electronically. Electrical or electronic communication directly between human nervous systems. This is the future for Telefónica, most certainly. Clearly, where this is heading is not just nervous system to nervous system, but brain to brain, so we can communicate in a much, much richer way. I have to say my wife is not keen on that. For some reason she feels, well, not keen in doing it herself. She feels that it is quite dangerous. I can't understand why. So I will need a partner purely for that experiment if there's any volunteers. So hopefully you can see where it's going. Hopefully you can see help for people with disabilities, but also hopefully you can see how all of us, if we want, will be able to be enhanced with technology as cyborgs in the future. Thank you very much.
Come with me. Sit down here with me. We're going to talk a little. Bueno, yo ya sigo en español.
Well, I'll continue in Spanish. I would like to ask you some things. Do you have any kind of implant? She wants to know if you have any kind of implant.
Sorry, at the moment, I don't have any implants. My students have some, which I'm jealous of, so I might have some. But I do still have some wires from the implant that I had before. When the surgeons took the implant out, they left quite a bit of platinum wire in my arm, and it doesn't bother me at all. Occasionally it sort of pops up, and I have to push it back in again. But apart from that, I don't have an implant that's doing anything. So I'm between implants. Yeah.
¿Y cuál sería?
And which would be the implant that you would dream the most? What's the maximum for you? What would that device do?
I believe strongly that we are going to communicate directly brain to brain, and therefore I would love to actually make it happen, the first brain to brain communication. They've done, a guy, Miguel Nicolelis, has done something similar with rats, but of course with rats you know to communicate is a difficult thing, but it looks very promising, and I think as humans, because you would know what's going on, then you would be able to adapt and learn, so that's something I definitely want to do, and I think we're not far from having everything ready, the technology to do it. Of course it will be quite dangerous because it's a brain implant and things can go wrong, but it will instantly satisfy a number of philosophical arguments, because there are those that argue we think in a language, and there are those that say no, we use a language purely to communicate. And so part of that, hopefully, we would actually know by doing the experiment. So it will annoy quite a few philosophers, if nothing else. So I think that's not a bad thing anyway.
Desde luego. ¿Cuándo se produce?
When do you think that this cyber revolution will take place? That moment in which it's to have an implant, an electrode will be something normal, and what will happen in the airports, for example, because we will go all through the machine and will go beep.
I think in some ways it's already been happening for a while, as we saw the example for therapy, for helping somebody with Parkinson's disease, and it is being used more and more for different problems with the brain, and lots of different implants. Heart pacemakers, a lot of people have artificial hips, so the different materials that are used are now well understood, and people accept that you can have implants. It's not such a big deal. In fact, some people, they want the implant because they can be a lot better. So I think for therapy, people are using them a lot more. For artistic purposes, like my students, there are quite a few people now that are trying different pieces of technology for artistic purposes, and doing all sorts of different things, or crazy things, I think. So there are lots of examples. I think where we don't have more examples is in this pure experiment for enhancement, as yet. Okay, I've been there. I didn't need it for therapeutic purposes. I did some experiments, and we saw there were good results. It could have gone wrong. It was dangerous to do what I did, but it turned out okay. Why there haven't been more of that nature since me, and why I'm the only one so far, I don't know. I'm surprised. I think maybe some academics in universities have too easy a life. They need to go and do a bit more experimentation. Hopefully it will be soon. I think the technology is there. I really think we have
the technology is ready.
The technology is ready. It just needs some experimentation. So maybe you would like to try something.
Why not?
So just a little bit of...
Podremos ampliar.
We could expand our senses. We could, instead of seeing in visible, in infrared and ultraviolet system. Do you think that implanting, for example, some kind of device, could we fly, for example, something that the humankind has always wanted? Could we fly?
I think you're talking about physical things. I have to say I'm more interested in the brain. So I will answer your question in a different way, because I don't know how many people have seen the film The Matrix, but in The Matrix, signals are passed down into the person's brain to make them feel happy, or the world is the world they're given from the computer, from the machine. And of course, that, I think, yes. I mean, in terms of thinking we're flying, which is all there is to it, then I would say yes. We would be able to have a machine which would send signals, and we think we're flying, or think we're doing whatever we want to do. And I think that's not a bad thing. Firstly, from a therapeutic point of view, because why be sad and down and upset when you could be happy? So you can have more of a future that you want. We do know a fair bit about stimulating pleasure zones in brains. A lot of work has been done stimulating pleasure in not just in humans, but a lot of work in animals. And in humans, the stimulator that is used to overcome depression, one of the positions it can be put in is where it stimulates pleasure. So I think things like that, to stimulate happier feelings, you know, let's all be happier, sort of electronic drugs, really. So I think why not? Yeah.
Bien visto, es verdad. ¿Y cómo evolucionarán?
And how will our brain evolve? Will it get adapted? Because if technology goes faster than the evolution, there could maybe some kind of problem there.
It's a very interesting question, I have to say, because there are two theories of evolution. One is the more pure Darwinian theory, which says we just evolve genetically, and a man and a woman come together and produce a baby which shares the genes, and that's all there is to it. There is also the Lamarckian theory of evolution, and what that says is if you do things in your life, then the things you do by habit, or if you have pieces of technology or whatever, will change your makeup, even change your genetic makeup. And then when you have babies, they will effectively evolve to be more in tune with the technology. So to be honest, I think, my own feeling is that the Lamarckian theory, even though it's not the English theory, but the Lamarckian theory is more what happens. And if that is the case, then very quickly we would evolve. Babies would evolve to be much more in tune with the technology, and their babies would need the technology to really operate well. But that is not really the Darwinian theory. And so much so that I have given presentations in Cambridge, and when I suggest that maybe Darwin didn't get it quite right, it's very dangerous to suggest something like that in Cambridge. So it really does depend on which theory is correct. And maybe we're going to find out, because if Lamarck was correct, very quickly we will really change. The brain structure will change, what we believe we can do will change. Maybe brains will grow even more because there's more input and more output. In terms of anthropology, there have been several stages where it looks like the human brain has developed very rapidly. It's grown over a very short period of time. This could be another one. This could really be another one, and I think it's more that link with technology will mean that the brain was, hey, now I can do lots more, now I need more input, now I go, and it will very quickly expand. And so our offspring in a few generations time, I mean it might be 10 or 12, but a few generations time, will have much bigger brains and much more interaction with technology. Buy shares in Telefónica, because as long as they get into this area in the future, the networking will be where it's all about, so in order to benefit from that.
Bueno, ¿te has encontrado gente que no quiere?
Have you come across people who don't really want that future where there's a merge between man and machine? People who think that this is completely horrible and that really don't appreciate it?
I think the answer mostly is no, because if you look at the therapeutic side of things, the way this technology can help people that are in pretty desperate situations is enormous. The opportunities are enormous. And when it comes to that new form of communication, it's tremendously exciting that we could. And I think people are interested in what is it going to mean? How could we communicate brain to brain? So generally I think there are people clearly that are perhaps a bit scared. I think I would be a bit scared, but that's what happens with science. You know, this is going to be a bumpy ride, but that's the exciting part of science, because we don't know exactly what's going to happen. But I think most people are very supportive. I've not had issues with ethical problems. We have to go through the appropriate procedures. I've had a small number of religious extreme people mainly from places like Texas, for some reason, who have sent me odd emails telling me I am some antichrist and things like that. But there have been more religious people who are very supportive, openly supportive. I was in a presentation, funnily enough it was in Cambridge as it happens, and somebody was criticizing me, but a man stood up who turned out to be the Bishop of Coventry. So he was a very religious, senior religious person, and he said it is vitally important that this research happens. First of all, God has given you the ability to do this research, so don't stop. It's important to do the research. It could help lots of people, but it could also change our lives for the better. So I have also religious support, and I think the religious support has outweighed the odd, crazy people who have sort of felt too strongly negatively.
Has comentado que
You mentioned that you got neurons to put together those little robots that move around, that are a bit clumsy in the beginning when they're babies, and they learn as weeks go by. Where did you get these brain cells? Where did you buy them?
Interesting point. Mainly we'd use rat brain cells, and I have to say these are taken from rat embryos. So there's a lot of animal research goes on in the University of Reading, and the rats are used for different purposes. We use the brain cells. So it's not specifically for our research at all. We're working with lots of other teams. However, for human brain cells, literally it is telephoning. There are a number of companies. They tend to be American companies, so I guess they are American brain cells, but it's as close as we can get to human, I think. As I understand it, they are from abortions, taken from abortions. So we can just buy them. I was surprised. We have ethical approval to do it, but I was surprised how easy it is to get human brain cells. And literally you telephone, and next day there they are, ready for you to use. It's a bit like ordering something off Amazon.
Una pizza, no?
But I think to say, yeah, the pizza, that's right, a delayed pizza, yeah. But I have to say, as far as the surgeons who we work with, any results that we get, if they are to do with rats, the surgeons almost dismiss the results. They're not close enough to the human brain for the surgeons to say this is important. So it is important when we're looking at Alzheimer's, which is one of the things we're specifically targeting. It's important to use human brain cells. We don't want to prove something, look, we can do this with rats, because we don't know if it's going to map to humans as well. So we say, oh look, we're able to retain memories by adding brain cells in a rat. The surgeons would say, no, that's not
Chimeras, no.
It needs to be human. So to really prove, to tackle dementia in this way, really it has to be human brain cells, I think, for the surgeons to sit up and take note.
¿Cuándo decidiste dedicarte a esto?
When did you decide to devote your life to this? When did you get that spark that made you devote your life to studying cyborgs?
As a professor, I was in a position where I could do it. Unfortunately, the technology became available. But before that, there were a number of factors. One, I enjoy science fiction, and when I was a teenager, there was a Michael Crichton. Michael Crichton wrote Jurassic Park and various other things. But he also wrote a story, The Terminal Man. And this was about a man having electrodes pushed in his brain. And as a teenager, it excited me very much. Not so much as a fictional story, which is what it was, but more that's got to be possible, that thing. At the same time, well, earlier, when I was about 8 or 9, my father had agoraphobia. This is the fear of open spaces. And he had it so bad he had to stop work and he was at home, and then he got confined to one room. He couldn't go out of a room. And in the end, they tried everything, but nothing would work. So they operated on him, neurally. And literally, he went into hospital, and as he described it, they drilled a couple of holes in the top of his head and cut out some of his brain cells. They did a leucotomy, a lobotomy, and it worked for him. So this is my memories of him, of how just small changes to the brain can dramatically affect a personality, completely in my father's case. So really I was inspired from that to try and do something to help people. There was also the input from science fiction, and then I found myself in a position where I could actually do it. I had the position where I could get ethical approval, and as a professor I could drive things forward, and hence it was tremendously exciting. And there was no way I was going to sit back and say, well, I could do it, but I'm not going to do it. I'm going to take an easy academic life and just work with equations and computers, because I wouldn't have been able to live with myself if I did that.
Pues para terminar lo que vamos a...
Well, to finish off, what we're going to do is to ask you some questions that we got from the social networks, through Twitter, through Facebook, with the hashtag TecnoRevolution and TecnoRevolución. So I'm going to convey some of the questions that the people from the network pose. This is Aurora Ferrer. In Twitter, her username is Aurora Ferrer, and she says that not too long ago, Hopkins theorized that in the future, brains will be replicated in computers. Do you think there's a possibility for this?
Computers. And it depends what you mean by computers here, because I mean one of the projects we're doing, of course, is growing brains. So the computer maybe could be made of silicon, but it could be a biological computer. In terms of silicon, philosophers have argued this. Can we and will we ever exactly replicate human brain cells and the human brain in technology, in silicon? I think we could get, I would agree with Stephen Hawking to an extent, we could get very, very close. That we take a brain cell and here is a very, very close replica. Whether you could do a whole brain, I don't know. But in his case, of course, Stephen Hawking, he has motor neuron disease. So part of his brain is perfectly okay, and part of his brain he has a problem. And I think where it could be useful is putting technological parts into the brain to overcome the problem. And that, I think, yes, I think that will be possible. So maybe he can be one of the first recipients. That doesn't mean it would operate in exactly the same way, but in his case you wouldn't want it to operate in exactly the same way. It's not to say it would be perfect, but at least if it did the main points, then it could operate. To actually model, to measure all the aspects of a human brain and replicate it in a technological brain at a particular instant in time all I will say is it's an interesting concept. I don't think it's going to happen this year. It's very difficult because of what's involved with doing that to imagine it ever happening, but strange things happen. So.
Bien, Alonso Isidoro Román
is asking through Facebook, aren't you scared that this technology could fall in the hands of genocides, for instance?
With any new technology, particularly this, because it's changing, going to change things, life-changing, it has very positive aspects, as we've been talking about, in terms of helping people and extending abilities, but it has potential negatives. We take nuclear power, and nuclear power has lots of positives as far as power generation, but when you look at nuclear weapons, you know, we hope they don't get into the wrong hands. And we've been able to live with nuclear weapons and reasonably control it. The problem is still potentially there, but we live with it. And I think and hope that this would be the same. We hope it doesn't get into the wrong hands or to be misused. There are potential negatives, potential hacking into somebody's brain, security issues, power down. Your brain depends on the technology, power is lost, and suddenly you haven't got part of your brain, your technological brain. So there are potential problems, pushing signals into the brain which become a virus, a biological virus, creating a biological virus. I shouldn't give examples how it could be used wrong, but we have to face it. Yes, there are potential negatives.
Maybe super soldados, super soldiers.
Super soldiers, for instance.
Well, but that, super soldiers, is both a positive and a negative, because at the moment we don't really want human soldiers to die. Now, if we look at what we have at the moment, and some soldiers dying, if now we say, well, we can actually build some soldiers, you know, we'd have either a technological or a biological brain, surely it's better for them to go into battle, and if one of them dies, isn't that better than humans die? You know, it's a positive and a negative. If they're on our side, then we would see it as a positive. I mean, even now we have, sorry to be a bit cynical about it, but that's how it is. I mean, even now we have drone planes, fighter planes, that don't have any human pilot on board, and they have very, very, if any, very limited human control. Most of the time they are in control of themselves. They have a mission. Human has a veto, but is not controlling them. That's the truth of the matter. And they have considerable firepower, typically 6 missiles, maybe 8 missiles, which the drone decides when to fire and when not, and who to fire at. So this is the technology that is being used already now. We already have part technological warfare. So super soldiers, one might see in a very positive light if it means that human soldiers are not going to be killed anymore.
Y para terminar,
And to finish off, we have a question from Oscar Gracia. He says, are you certain that it is a good idea for someone's wife to read your thoughts? How did that experience work out for you?
The experiment with my wife was absolutely tremendous. When you think about it, I mean, as a husband and wife, you can be very intimate. I mean, if you have sex is an intimate act. But we were sending signals between our nervous systems. This was even more intimate. And I have to say, we felt close. It was fantastic for her to be part of that experiment. I think we felt we understood. We did send signals for a bit of fun during the experiment that other people didn't know about. But we knew about it. And, wow, how powerful is this? Absolutely incredible. But it was tremendously exciting. And I think this, for my wife, this is a bit of a worry for her, because I say I want to have another implant and connect up, and she is worried that I will connect up with a very beautiful woman, and she knows how intimate it is, and I think she's not too sure about that. There we go. She might trust the beautiful woman, but I don't think she trusts me completely. No, it's a very intimate act, and I think it does make me feel that if we started to communicate that way more generally, we would feel a lot closer. as people. We would start to understand each other a lot more, and we would relate with each other a lot more, I feel. And hence it means a lot more if we communicate in that way.
Pues con este bonito mensaje nos quedamos y
we're going to finish off with this beautiful message. Thank you so very much for having visited us in Spain and for having shared all the thoughts that you have shared with us, Kevin. Thank you very much.